We've mentioned the biennial variability a few times already, and we had seen this before of the All India rainfall, the wavelet spectral analysis. So these are the periods here, and you can see the biennial variability in those bands, which disappears sometimes with lower frequencies appearing, maybe ENSO time scale, maybe lower frequencies, multi-decadal time scales, and so on, which is also seen here in terms of the 2 to 8 year variability. We had talked about this period as the time when the relation between the southern oscillation and the monsoon disappeared, and people thought maybe Walker was completely wrong, and so on. And then Normand came along and said monsoon actually leads the southern oscillation, so we cannot really rely on it as a predictor, etc. Right? Now let's get more specifically to the biennial variability. This is also observed in the Australian rainfall, as I mentioned before with the Harry Hendon figure, Indonesian temperatures, etc. So there is that transition from quasi-quadrennial El Nino time scale to the quasi-biennial time scale through the Indonesian seas. Neville Nichols was one of the first to look at it and propose a theory. He said throughout the year, above normal equatorial SST will tend to decrease the atmospheric pressure of the tropics and subtropics. It's proposed that the anomalous pressure pattern thus produced will cause variations in the original SST anomaly. So you start with the SST anomaly, associated pressure anomaly, and then the pressure anomaly itself is able to switch the SST anomaly to give you that quasi-biennial time scale. The sense of the variation, increase or decrease in the SST anomaly, will depend on the direction of the prevailing wind, which itself varies seasonally. So the monsoon winds themselves over Indonesia also change directions. Thus, during part of the year, a positive pressure anomaly will be associated with an increase in SST, like there is a subsidence, while during remainder of the year, same pressure anomaly would be associated with a decrease in SST. So you have other interactions happening because of the wind and kind of the Vichy feedback, if you will, wind-induced surface heat exchange feedback. So I took this Indonesian rainfall and wind figure just to make that point. Here we are looking at JJA from TRIM, and this is the NCEP, TRIM and NCEP JJA, TRIM and NCEP SON, but basically focus on the change in the wind directions. When you have the southwesterlies over the Indian Ocean or the Indian South Asian monsoon region, you have winds turning around and becoming almost let's say westerlies or northwesterlies over Indonesia, and then the direction completely changes when you have northeasterlies over India setting up. You have winds becoming almost southeasterlies over Indonesia. Associated with that, you have these rainfall seasonality. This is just comparing precipitation over different periods. Nonetheless, the region of the Indonesian seas has high rainfall during its summer or boreal winter months, and during boreal summer month it has a minimum, and then it turns out that the interannual anomalies are also largest during the boreal summer months over Indonesia, and that gives you a sense of the correlation that I had mentioned before between Indonesian rainfall and winds over the eastern Indian Ocean, and potential mechanism that would probably relate this variability to the Indian Ocean dipole over here. But nonetheless, Neville Nichols was focused on this region because he started with the Australian monsoon, and that's how he had proposed it. And the other big idea came from Jerry Meal based on his modeling work. And again, these are just like before when we said MJOs are ENSOs, there are multiple theories, which means there are still some open questions. So it's not a bad thing. It just means that there is still some work left to be done. So this is showing a cycle of how you would get quasi-biennial or biennial variability. So let's say you started with warm SSTs over the tropical Indian Ocean. That is typically associated with strong East African rainfall and decreased Siberian high, decreased snow, and you have warm temperatures anomalies over there with this zonal gradient of cool SSTs over the Indonesian seas, sorry about that, and weak Australian monsoon here, and you have warm SSTs on the Pacific side. And that warm SST in the winter months is argued to give a strong monsoon in the following South Asian monsoon season. Those strong winds associated with the strong monsoon would give you cool SSTs over the Indian region and warm the SSTs over the maritime continent and cool on the other side. Okay, this is based on model diagnostics, and there is some evidence from observations that this could work. And then from JJA of 0 for the following DJF plus 1, you are starting with the cool SSTs, increased Siberian high, increased snow, and all kinds of other adjustments, then adjustment of the zonal SST gradient, and that cool SST would then give you weak monsoon, weak winds, and then warm the SST in the following year. Many questions remain open. For example, how a warm SST anomaly would persist long enough to give you monsoon signal in 6 months later, or at least more than 3 months later. You know, you have to go from DJF through MAM into JJA, and how this signal would persist back onto DJF and so on. But we have seen that over the Indian Ocean, the SST and SSTs do have a persistence from DJF to JJA, and that's not so strong over the Pacific. So maybe there is something to it, but these are not always so obvious. The relation between African monsoon, South Asian monsoon, and the Australian monsoon, and so on. They are, when you take long time series and you do spectra and you get peaks, but that doesn't mean you see a systematic biennial period. For example, we had seen this Indian and Australian monsoons, and you can see here that we already talked about how the South Asian monsoon has a very low variability of only plus minus 10% around the long-term mean, whereas the Australian monsoon has a larger variability. You don't necessarily see a strong relation. You see here a weak monsoon, weak Australian monsoon, but the relation is not very robust, and it's not immediately clear if there is really a quasi-biennial signal here. The decadal signals may be more obvious than that. Okay, so this is from 1870 to 1930, and this is from 1930 to 1990. So you can see there are decadal variabilities, stronger variability here, weaker variability here, and the same for the monsoon, weaker here, stronger here, and so on, which we already saw. So is it obvious that the quasi-biennial variabilities and the relation between the Indian and Australian monsoons are robust? Not quite, but the theories are existent nonetheless. So the question is, can there be a self-regulation of the ocean heat transport, monsoon winds, monsoon rainfalls, and so on? We saw one version of this already. So we have a strong boreal summer monsoon, which we expect to drive strong southward Ekman transport across the equator. So we're going from the warm summer hemisphere into the winter hemisphere. But here we're talking about anomalies of monsoons. A strong boreal summer monsoon is an anomaly from a long-term mean, and that would give you stronger monsoon winds. That relation is robust. That would give you stronger southward Ekman transport, which does respond fairly quickly, even though near the equator the time scale of Ekman adjustment is 1/f. But we already argued how we get smooth Ekman transport across the equator. And if you have weak boreal summer monsoon, you have weaker monsoon winds, so you have weaker cross-equatorial transport, and you have a warmer winter hemisphere in the south of the equator. Okay, so because you have weaker winds and so on. So this is kind of the argument. Net Ekman heat transport increased in this case, which would somehow leave the Indian Ocean, North Indian Ocean colder for the next season, next year. Well, that survival of the anomaly from one year to the next is not being clearly demonstrated. How it would remain for 1 year through all these seasonal forcing changes and the desert outflow, dry northern winter winds and so on is not so obvious. But at first sight, with forced ocean models, you will get these kind of Ekman transports reduced for weak boreal summer monsoon and increased for strong summer monsoon. Okay. The other theory maybe I should come back to in the next podcast and leave this one here. So the Neville-Nichols hypothesis of the SST pressure relation changing because of the change in the seasonal winds is one thing, and this idea of the Ekman transport and the Neville-Nichols' propagation system of weak and strong monsoons is the other one. Alan Clark has proposed Western Pacific interaction which remotely forces the Indian Ocean biennial variability, and he says that Indian Ocean cannot generate its own biennial variability, but this is rejected because we have fairly strong biennial variability in the Indian Ocean. The other one that remains to look at is the interactions with the El Nino and Southern Oscillation, which we will do in the next podcast.